begin?
I have a couple of questions on the homework.
Sure. Okay.
They're kind of small. So
Sure.
on question 6, part B, it says to make a function that assigns to each positive integer its greatest decimal digit, but
Oh,
integers don't have decimals.
what
So
problem is this?
6B.
6b. I haven't talked about decimals, so maybe I should just tell my grader to not grade that one. But go on in any case. So
Yeah. So it basically was confusing me. I ended up putting in as the codomain 0, 1, 2, 3, 4, all the way up to 9.
mhm.
Thinking that might be it, but it also kind of like an integer can't have a decimal of 9, right? Uh, and
Oh,
so,
so it's saying like it's ones place, right? Like,
well, it's saying assign the greatest decimal digit. So if it like had, I interpret that as if you had like 3.19, you would assign 9 to it because 9 is the greatest digit, decimal
uh-huh.
digit.
I see. I thought I had avoided asking questions about decimal expansions, but if I fail to do that, then I apologize. 6b, the function that assigns to each positive integer its largest decimal digit. Yeah, I think that what you described, having the codomain being 0 through 9, is perfect.
Okay. And so kind of tangential to that question is that uh, though it can be zero, like kind of uh, when you're given a problem like create a function with that assigns a certain number to each part of the domain,
Yep.
like for that last problem, my interpretation is that an integer can only have a decimal of 0, right? It can't have 1, 2, or 3. So when couldn't I possibly come up with a different codomain for that kind of function?
So are we still talking about the same problem or a different one?
Kind of, but more in a slightly more like general term is that if I'm giving a problem like this to where I'm asked to create a function that assigns certain values to a specific domain, isn't there multiple possible codomains I could come up with?
Yes, that's certainly true. You could also have defined this function as a function from from integers to integers, but then the range would only be 0 through 9 in this example. So there is a very large variability of the codomain that you can assign to a function, even if the range stays the same, right?
Okay, cool.
So yeah,
Um,
there's a large variability in codomains.
awesome. Um, and just a quick, are we going to be doing any of the proofs that involve functions in class?
Um, I mean, we have been doing some, and today I'm going to do some more in section 2.5.
Okay.
But do you mean like the injectivity, surjectivity, and composition functions?
Yeah.
I was not planning on doing those today, but maybe we can spend a little bit of time on that if people would like for me to do that next class.
Okay, cool.
And Janae, that's also a good question. So they're kind of ambiguous. So I personally will always write z greater than 0 or z greater than equal to 0, because these tell you exactly what is meant. Z plus, I think in the textbook refers to this one. But I try to use these notations so that it's perfectly clear and that there's no ambiguity. Okay, so we are recording, good. So what I want to remind us is of what we did last time. So last time, we discussed function composition. So we discussed how can you compose functions. And then we also discussed the idea that a bijection if I have a bijection f from a set A to B, this is equivalent to the function f being invertible. Which in this case, what does it mean for f to be invertible?
Doesn't it mean there exists a function g such that the composition of f and g is the identity function?
Yes, in both ways. So there exists a function g from B to A such that f composed with g is equal to the identity function on B, and g composed with f is equal to the identity function on A. So the picture, of course, is you have your function f, which goes over this way, and you have your function g, which goes over this way. And if I compose f with g, that means first I go over by g, then I go over by f. So that's a function from the set B to the set B, and I want that to be the identity function that sends every element back to itself. And similarly, I want g composed with f, namely first you go over by f, then you go back over by g. I want, okay, don't know what happened there, but it seems like something went wrong with Zoom for a little bit, or maybe it was me, I'm not sure. I don't think it was me. Sorry about that. Can everyone hear me? Am I still good? Okay, cool. So we discussed how bijections are the same as invertible functions. Okay, and then the last thing that the last things that we discussed are that bijections are the right way to measure cardinality. That is, we defined, so by definition, well, we defined cardinality of finite sets by just the number of elements in them. But we say that A and B have the same cardinality if there exists F, a bijection, A to B bijection. And okay, I'm audible. And just as a kind of additional note, and this I think is going to be a very reasonable thing, also we have the cardinality of A is less than or equal to the cardinality of B if there exists an injective function f from A to B injective, and cardinality of B is greater than or equal to cardinality of A if there exists G from B to A surjective. And we can take these as part of the definition, but they also are very reasonable definitions, right? Especially on the level of finite sets, because I can't have an injection from a larger set to a smaller set. And similarly, I can't have a surjection from a smaller set to a larger set. Any questions on this kind of setup for cardinality?
I have a question.
Sure.
So when you said the cardinality of A is less than or equal to the cardinality of B, isn't that the same thing that's written on the second line?
Oh, shoot, yeah. Yeah, these are the same thing. So I can either say that I have the cardinality of A is less than or equal to the cardinality of B if there's an injective function, and the same relation holds if I have a surjective function going the other way.
Oh, okay. Thank
Yeah,
you.
so I don't think I have, but I didn't assign any homework on 2.5, did I? That was due today? Just 2.3, okay. So you're saying that this information would have been helpful, but okay. Val, maybe we can chat after after class and make sure that you didn't do the wrong homework or something like that. But in any case, yeah, I only assigned stuff from 2.3 to be due today. But you have several hours left to do it. I think the deadline's at 6 p.m. today. So if something is amiss, then we can chat. Okay, so what I want to do as a warm-up, I want to do several really cool examples today. The first thing that I want to do is kind of similar to what we did last time. Remember that a set is countable if it has the same cardinality as the positive integers. Okay, so what I'm going to do is let's show that the cardinality of the positive integers is the same as the cardinality of the integers. So in other words, yeah, for our attempts to understand what the size is of different sets, these sets should be thought of as being the same size, even though Z is a proper subset, or the positive integers are a strict proper subset of the integers. I'm cutting out again. Am I still, is it better now? Am I okay? I don't think anything. So am I back?
You indeed are.
What a mess. I'm so sorry about this, y'all. Yes, Alex, that's correct. I always write them this way because I feel Z plus is a little ambiguous. So yeah, they're the same. Okay, so how do I prove something like this? What do I need to do?
Find a bijection between the two.
Right, we want a bijection. Task. Find a bijection. And I'm going to show you what the bijection is. So I'm going to list out the integers, 0, 1, 2, 3, 4, 5, 6, etc. And -1, -2, -3, -4. Here's my good old number line. And then I'm going to tell you by putting numbers on top what I'm going to assign to everything. So 1 is going to be assigned to 0. 2 is going to be assigned to 1. 3 is going to be assigned to -1. 4 is going to be assigned to 2, 5, 6, 7, 8, and so on and so forth. Or in other words, this bijection that I'm trying to describe is kind of by going back and forth. I bounce from here to here, to here, to here, to here, back and forth. Okay, and I do that forever. Another way to say this, what we're doing is giving a bijection with the positive integers is the same as writing out the new set in a line. So I could also say this as 1, 2, 3, 4, 5, so on and so forth. And then I do 0, 1, -1, 2, -2, 3, -3. Is it clear what function I'm trying to describe with these pictures? Does anyone have an issue with what function I'm trying to describe here? It turns out I can, yeah. So in this case, I can write out the actual function. So here, I'm going to send f from z greater than 0 to z, and it's going to be a piecewise defined function. X is going to be mapped to z over 2 when z is even, or sorry, x over 2 when x is even, and it's going to be mapped to x minus 1 over -2 when x is odd. So you see that that's exactly captured here. When I have like all of the positive integers are going to be assigned even integers, which are twice what they are, right? So what is the preimage of 4? 8. What is the preimage of 5? 10. What is the preimage of 6? 12. So that's this chunk. And then for 0 and the integers that are negative, I'm going to be assigning them odd positive integers that fit this relation. If I multiply this by -2 and add 1, I get 5. If I multiply this by -2 and add 1, I get 7. If I multiply this by -2 and add 1, I get 9. So the way that this function is literally written out is piecewise defined. And my claim is that this is a bijection. Could I do f from z to z plus as well? Yeah, I could just take the inverse function, right? Like here is a function going this way. As long as this function is a bijection, then I have an immediate inverse function by going the other way. And yes, so that's also a reasonable thing that I could do. If I want to show that z has the same cardinality as z greater than 0, I could also provide a bijection from z to z greater than 0. That would also be a valid way to prove this. Now, this is a bijection and I can prove it rigorously, but what I'm asking for you to be comfortable with, at least for this lecture, is this way, this kind of loose, slightly less rigorous way of describing a function. Are there any questions about this? Now, I haven't proven to you that this is a bijection. However, I claim that you can show, one, that this function is surjective, which should be kind of obvious because every integer will eventually get hit by this process. Y'all, I simply do not know what to do about this.
I think Josh is doing it.
I do not know what to do about this. Okay. Well, anyways, perhaps that cut me off in the middle of a reasonable explanation. But are we at least okay with the idea that I've produced a bijection here? Seems okay? Okay, great. So now I'm going to start getting into the 3 kind of heavy hitters of today. Great. I'm delighted by everyone's responses. Today will feel a little bit lackadaisical perhaps, but I think that we're at a place where we can understand these proofs that I'm writing. Okay, so my next interesting example. So what I'm saying is that I don't want to take the time to show that this function is a bijection. If you wanted, so I can tell you like what would be acceptable on a test. I would accept this picture on a test for this sort of bijection. And I'm saying you can make this totally rigorous by showing that it's surjective, literally, and then showing that it's injective on each piece, because on this piece, this is a strictly increasing function. And on this piece that is on the negatives, it's a strictly decreasing function. But I'm not going to actually go through with the full proof of bijection for these problems that I'm going to do today. Or at least I'm not going to do it for the next one. Okay. So the next example, yeah, exactly. Pictures are back in. The next example is that the rationals, or in this case, the positive rationals, are countable. Okay. So this is saying that the positive integers are somehow the same size of set as the positive rationals, even though there are infinitely many positive rationals in between each positive integer. And what I do is we set up a bijection. So here's where I'm going to, thank you. I'm kind of proud of my Q's and Z's. I'm most proud of my L's if I want to do something like the Lagrangian. Anyways, so what I'm going to do is I'm going to set up a bijection. All my other letters are trash, but at least my Q's and Z's and L's are good. Okay, so here's the bijection that we're going to do. First, I'm going to list out all of the positive rationals, and I'm going to do that in this way. I'm going to list out all of the numbers or all the integers with ones in the denominator in the first row. So 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1, 6 over 1, etc. Then in the second row, I'm going to list all of the positive rational numbers with a 2 in the denominator. So 1 over 2, 2 over 2, 3 over 2, 4 over 2, 5 over 2, 6 over 2, etc. And with the third row, I'm going to do the same with 3. 1/3, 2/3, 3/3, 4/3, 5/3, 6/3. And then with 4, 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, and I'll do one more row with fifths. 1/5, 2/5, 3/5, 4/5, 5/5, 6/5, etc. Do we agree that every positive rational number will appear at least once on this list? Yeah, actually, each positive rational number will appear many times on this list. For instance, 1 over 1 is the same rational number as 2 over 2, is the same rational number at 3 over 3, same as 4 over 4, right? All of these are ones here. But at least what I have here is I have all of the positive rational numbers here. Now I'm going to describe to you the bijection that I'm going to do. The bijection is going to go like this. I'm going to move in diagonals. I'm going to send the positive integer 1. God, I don't know what is going on. This is so frustrating. Am I okay now, or is it going to die on us? Yeah, I'm about to get snapped. Okay. Is it my connection? My connection is good, apparently, or at least my computer is telling me my connection is good. Okay, whatever. I just have to continue. The show must go on. So I'm going to go in diagonals. So I'm going to assign 2 to this one. Then I'm going to assign 3 to 1/2. Then I'm going to assign 4 to 1/3. Well, I'm going to skip right over 2/2 because I've already counted it. And I'm going to assign 5 to 3. And then I'm going to assign 6 to 4. Then 7 goes here. Then 8 goes here. Then 9 goes here. 10 goes here. Well, 2/4 has already been counted because that's 1/2. So I skip over 2/4, and I skip over 3/3, and I skip over 4/2, and so 11 will go here. So this function is pretty much impossible for me to, thank you everyone for telling me what is wrong with my, my bandwidth. So this function is very difficult to write down in symbols. But nonetheless, what I'm claiming is that this does indeed define a function from the positive integers to the positive rationals. Does anyone have a question here?
I have a question actually.
Yeah, sure.
So how could it be injective if you have 1 pointing to 1 over 1, but then you have, what is it? 5 pointing to 2 over 2 when those are the same values?
I don't have 5 pointing to 2 over 2. I skip
Or
over
4,
2
sorry.
over 2
Oh,
because it has already been
okay.
counted. I'm skipping over all of the non-reduced fractions.
I gotcha. Thank you.
That's why it's injective. So the idea of this is I'm tracing through this path. I'm snaking through this diagonal path, which will eventually touch every number on this list because every point on this list is on some diagonal coordinate. And then the point is, if the fraction is reduced, then I count it. If the fraction is not reduced, then I skip over it because it has already been counted. Is this okay? Right. So what I will say is that if I ask you to show this bijection on a test, this is the picture that I expect. I don't expect you to write anything down, but this is the picture to understand why there's a bijection from this set to this set. So now we see that the rationals, or at least the rationals greater than 0, are countable. And it turns out it's pretty easy to show that actually all of the rationals are countable. Yeah, 8 is assigned to 2/3. That's correct. Any questions here? Okay, so that is not correct. It is not correct that infinite sets are, so first of all, these sets are not equal, right? Because there exist elements in Q that are not in Z. So already I know these sets are not equal. What I did show is that these sets have the same cardinality. Now what I will show is that there is a set that is of a different cardinality. Yeah, thank you, Val. This is cool stuff on this exact topic. Okay, first example of something that's not countable. The real numbers from 0 to 1, where I include 0 but I don't include 1, is not countable. Okay, so first, before I get into this proof, I want to make a remark. Every real number in 0 to 1 has a unique decimal expansion if we do not permit repeating 9s at the end. Like 9999, this thing going on forever is forbidden. But as long as we kill repeating 9s, then decimal expansions are unique. So for instance, 0.999 repeating forever this is the same number as 1, and these obviously have different decimal expansions. But the remark that I want to make is that if you kill tails of repeating 9s, then we have unique decimal expansions. Okay, so my proof is by contradiction. Proof by contradiction. Assume this set 0 to 1 is countable. What can I do if this set is countable? Well, if this set is countable, then I can write down every element of this set in a list, starting with one element and going on down the page. So if this is countable, then there's a way to list all of them. So here's 1, 2, 3, 4, 5, 6, 7, 8, going on forever. And 1 will be associated to the number with decimal expansion A11, A12, A13, A14, going on forever. The second number will be assigned to some number in here with decimal expansion A21, A22, A23, A24, going on forever. Similarly, the third number will be A31, A32, A33, going on forever, similarly. Do we agree that if I assume that a set is countable, that means that I can write them out in a list like this, such that every number inside this set appears somewhere on this list? Right, this is kind of what it means. If I say that I have a bijection between the positive integers and this set, that means I can match each positive integer to an element of this set, and moreover, every element of this set appears somewhere on the list. Okay, so what I'm going to do is I'm going to build a number which lives inside this set, which is not on this list. So for contradiction, I will build a B inside the interval from 0 to 1, which is not on the list. And this, of course, will contradict the assumption that this thing is countable, because if this is countable, then I assume that every number inside here appears on this list with some decimal expansion. So I define a new number, B is equal to point B1, B2, B3, B4, going on forever, such that B1 is equal to 4 if AII is not equal to 4. And, sorry, BI is equal to 4, and then BI is equal to 5 if AII is equal to 4. So let me do an example, okay? So example, let's say that this set was countable, and let's say I had like 1.12357 repeating, 0.78635 repeating or going off into infinity, 0.44455 repeating, 0.55654 going on forever. Let's assume, I'm just trying to show you how I'm building this number B. How I'm building this number B is I'm looking at the diagonal and I'm saying, okay, I'm gonna build a decimal expansion for my number B, and I'm going along the diagonal, and if the first element on the diagonal is not a 4, then I write a 4. So since 1 is not 4, I put a 4 first. Since 8 is not a 4, I put a 4 second. Since the third decimal along this diagonal is a 4, I'm going to put a 5 instead. Since the fourth element along this list is a 5, I'm going to put a 4 for my next element. And then this continues to infinity. So every single decimal is determined of B. Let's do one more thing. If I had 7, 8, 9, 6, 4 here as my next one, then since the fifth term in the diagonal is a 4, the fifth term of my B has to be a 5. Now I notice the point here, B disagrees with every number on the list. B, so I claim B cannot be on the list. Because if B were a number that was on the list, then it would have to agree in every place with the decimal expansion of that number, because decimal expansions are unique once we forbid repeating 9s. However, by the way that I have built B, by its very construction, B will disagree in some decimal place with every number that appears on this list, because I built it with that purpose in mind, and I was able to build such a number, right? B is not the first number on the list because the first number on the list has a decimal digit of 1 in the first place, whereas B has a decimal digit of 4 in the first place. So these are not the same. Can B be the second number? Well, no, because the second number has its second digit being 8, whereas the second digit of B is 4. So these cannot be the same number. Could B be the third number on the list? No, because for the third number on the list, its third digit is 4, whereas B's third digit is 5, et cetera, et cetera, et cetera. So we see that B cannot possibly be on the list. Yeah, I agree. This is a really cool collection of results, a really interesting collection of results. And yeah, this is some head-hurting stuff for sure. Okay, so what we can conclude is that the cardinality of this set, 0 to 1, is strictly greater than the cardinality of z greater than 0. So this set is not countable. And in particular, you can kind of imagine that the real line is built out of stacking these end to end to end. So we also get the corollary, R is uncountable. So what we have seen is actually there are at least 2 different sizes of infinities. There's one size of infinity, which is a set which is bijective with the positive integers. And that size of infinity is called countable. And we've seen several sets that are countable. The rationals are countable, the integers are countable, the odd integers are countable. Yes, it's not quite useful to always think about more or less, but the point is there is no bijective function between the integers or the rational numbers and 0, 1. So in some sense, yes, this is correct. The interval from 0 to 1 has somehow more numbers than all of the rationals because it is of strictly greater cardinality. Are we okay with this example? Yes, there are. They're called they start using Hebrew letters. So Aleph null is the symbol for countable, I believe. And then Aleph 1, I can't write Alephs, but Aleph 1 is the cardinality of the reals, and so on. Okay, I've got 8 minutes to do my last proof, so I want to kind of go to it. Okay, my next thing that I want to say is the following. This is called Cantor's theorem. This is called Cantor's diagonalization argument, and then here's a theorem of Cantor. The cardinality of the power set of S is always greater than the cardinality of S. In other words, if I want to make bigger cardinalities, I can take power sets. So essentially what I'm going to prove is we will show that there exists no surjective function from S to the power set of S. Okay. So before I launch into the actual proof, let's examine an example. So we're going to look at the following thing. Let f be a function from a set S to its power set. Then we can produce an interesting subset of S called T. And this is going to be the set of all elements, S and S, such that S is not inside f of S. So this is a confusing definition at first, and so I want to give some examples, okay? So let's start with the power set A being equal to the set containing 0 and 1. And then what is the power set of A? In braces here. This is the set T, is the set of all elements in S such that the element S is not inside the subset that it is being mapped to. So what's the power set of A? It's the empty set, it's the set containing 0, it's the set containing 1, and it's the set containing 1, 0. Okay? So what I want to do is I want to draw some functions, 0, 1, empty set, 0, 1, 0, 1, and then let's find out what this set T is. So someone tell me a place to send 0. Where should I send 0? It doesn't matter. You can tell me anything. Yeah, let's send 0 to the empty set, and then where should I send 1? Sure, why not? We'll send 1 to the set containing 1. Okay, so now what I'm going to do with this function is I'm going to look at each element in here. I'm going to check the subset that it's sent to, and I'm going to say, is this element inside the set that it's sent to? So is 0 inside the empty set? No. So I know that 0 is inside T. Next question, is 1 inside the set containing 1? Yeah, 1 is inside the set containing 1, so 1 does not satisfy this condition of being in T. So in this case, T is just the subset consisting of 0, the set containing 0. Let's do another example. Someone give me a different function from 0 to 1 to the same, to its power set, empty set, 0, 1, 0, 1. Where should I send 0 for a new function? Sure, we're going to send 0 to 1. And where am I going to send 1 to? Let's send 1 to the empty set, just for fun. Okay, now when I build my subset T, what I do is I look at 0 and I say, is 0 inside the subset containing 1? No, 0 is not inside the subset containing 1, so 0 goes inside the subset. How about 1? Is 1 inside the subset, the empty set? Also no. So in this case, the set T is, T is the set 0, 1, which of course is a subset of A, namely it's the whole set. I'll do one more example. 0, 1, I'm going to send 0 to the subset containing 0, and I'm going to send 1 to the subset containing 1, and then I've got 0, 1, empty set. So now my set T, well, I take 0, I say, is 0 inside the subset containing 0? Yes. Is 1 inside the set containing 1? Well, yes. So in this case, T is equal to the empty set. So now with these examples, does this set T that I build out of the function start making more sense? I'm hoping for a yes, but if I'm not going to get a yes, I would love a question. In this example, T is the set containing 0. It's not the empty set because 0 is mapped to the empty set and 0 is not an element of the subset that it's being mapped to. So this is different from this example because in this example, 0 is mapped to the set containing 0. And since 0 is an element here, it can't be in the set T. Notice T is a subset of A and also an element of the power set P of A. My next thing to observe is the following. In this setting, when I drew up this function, was the element containing 0 hit by my function? No, right? Nothing hit 0. In this next example, was the set 0, 1 hit by this function? Also no. Here is T as an element of the power set. Lastly, here, T is equal to the empty set. Is T hit by this function? Also no, right? Nothing got sent to the empty set under this function. So the idea here is that when you set this thing up in this way, it is impossible to hit the set T. So now that we have this example, let's go to the proof. So we are going to prove that no surjection exists from A to the power set of A for any set A. And what we're going to do is proof by contradiction. Assume that f is a surjective function from a to the power set of a. And let t be equal to the set of all a in a such that f of a, or such that a is not inside f of a. This is the same set T that we described last time. By surjectivity, what do I get? T is a point or an element of P of A, right? So if my function f is surjective, what does that mean? There must exist an M in A such that f of M is equal to T, right? Do we agree that T, being an element of the power set of A, must be hit by this function f if f is surjective? Okay, so now the question is, there are two options. One, either M is in T, or two, M is not in T. Let's examine the first one. If M is in T, by definition, this must be satisfied. M is not inside f of M. But what is f of M? T. Thus, M is in T and M is not in T. This is a contradiction. Let's try option two. Let's say M is not in T. What does it mean if M is not in T? If M is not in T, then this condition is not satisfied. So I know that M is inside f of M. But once again, what is f of M? But that's T. Thus, M not in T and M is in T. Contradiction. So what I have built here is a subset T of A that cannot possibly be hit by any surjective function f from A to power set of A. Thus, no surjective function from f from A to the power set of A can ever exist. What this means is that I actually have a whole hierarchy of infinities, because I have one hierarchy of things that are greater than 0. But I know that the cardinality of this is less than the cardinality of the reals. I proved that today. But by this proof, the cardinality of the reals is less than the cardinality of the power set of the reals. And this must be strictly less than the power set of the cardinality of the reals. And this goes on forever. So you can get, there's this whole hierarchy of different infinities such that between any of these different sets, there never exist surjections from here to here. There are no surjections from here to here. There are no surjections as you try to go up. So we have this whole hierarchy of infinities that we can examine and contemplate here. I'm now 6 minutes over, but this proof is kind of worth going through. Yeah, I'm sorry if today's thing were blurry. I can try to post pictures. Yeah, sure. Any questions about this? I know that I've held you all quite too long, but well, I have office hours tomorrow, and I'd be happy to chat with y'all tomorrow about this material. I'll send out some emails about where we're going next. We're going to go to a different chapter after this, well, I'll probably do some examples of functions in the next lecture, and then we'll move on to a different topic. I'll send that information out in an email. Any questions? Okay, have a nice day. Thanks for bearing with the technical difficulties that I was dealing with today.
Thank you.
Yep, thank you.
Thank you.
Yeah, of course, thank you.
Sorry, excuse me. I do just have one really quick question.
Yeah, sure.
I wasn't sure. I missed Monday's lecture,
Okay.
and I wasn't sure where to find the recording. Where do you upload those in Sakai?
They're all on YouTube. I can send you the link.
Oh, okay. Thank you.
Yeah, sure. I'll send you the link right after class.
Right.
Rohan, do you have a question? In that case, I'll probably end.